All right, everyone. Thank you for joining and welcome to the first installment of the O-Chem Simplified lecture series. Now, for those who are not familiar with the format of these lecture series, we're going to be diving into the concepts and the foundations, the understanding the basics of very important parts of organic chemistry that you're going to be seeing inside your classroom and also during your exams, whether it be an actual semester exam or a graduate exam such as your MCAT, your PCAT, or your DAT. So the purpose of this lecture series is to really enforce the knowledge that needs to be known before tackling practice problems. The biggest mistakes most people run into when they first start organic chemistry is that they simply just want to memorize, do a bunch of practice problems, and then go take the test. But there are many different shapes, many different molecules that can be drawn, right? So if they throw a curveball at you, will you be able to answer that question? All right. If you have a good understanding of your foundations and your basics, then the answer will be yes. So without further ado, let's go ahead and dive into the first O-Chem Simplified lecture series. Hey guys, forgot to mention that this is the voice of Josh Paul, the founder of O-Chem Simplified, and I will be going over the lesson plan for the intermolecular forces. So, to begin, we're going to first cover the definition of an intermolecular force, right? So, before we can even dive into anything, we first have to understand what intermolecular forces are. Then, we're going to dive in very quickly into the difference between intra and intermolecular forces. Moving on, we're going to define the types of intermolecular forces. All right. Your main types of intermolecular forces are going to be London dispersion, dipole-dipole, H bonding, and ionic bonding. Unfortunately, to understand some of these intermolecular forces, knowledge of periodic trends needs to be set in foundation. So we're going to do a quick review before we dive into those different types of intermolecular forces. So without further ado, let's dive right in. Okay, so the definition of an intermolecular force, right? Inter means between, right? And a quick note, IMFs is just a short way of us in the science field of just, denoting or abbreviating intermolecular forces. Now, inter means between, right? So intermolecular means between molecules, right? And intermolecular forces means the attractive forces between molecules, right? So when you have two molecules together, right, or different, whether they're the same molecule or different molecules, there's going to be a certain level of attraction between those molecules, right? But why? What is the reason why there's an attraction between those molecules? Take a second and think about this. So, guys, if you remember from Gen Chem, attractive forces are formed due to differences in electronegativity between atoms, right? And those differences in electronegativity causes, right? It causes there to be dipole moments, meaning one side of the molecule or the atom has a certain charge, and the other side, the opposite side of the molecule or atom, has the complete opposite charge, right? So that when you have those attractions and you have many molecules together, you're going to have counteracting charges that are going to be attracted to each other, right? So that is the reason why intermolecular forces exist, because of electronegativity differences and dipole moments, as we will soon visualize. All right, so let's take a look at what the actual intermolecular forces are, right? So first off, you have London Dispersion, otherwise known as van der Waals forces or induced dipole. Typically, most people just write LD shorted for London Dispersion. Right? Now, that is the weakest intermolecular force. The second weakest intermolecular force is dipole-dipole. Right? The second strongest intermolecular force is hydrogen bonding, otherwise denoted as H bond. Right? And then the last or the strongest type of intermolecular force is ionic bonding, right? So we'll go into further detail and visualize what's going on when we actually are saying these attractive forces between molecules. So, say for instance, we are dealing with helium, right? Helium, as we know, has two protons, two neutrons, and two electrons, right? So, as you can see with those two molecules or those two elements of helium on your screen, right? The circles inside the smaller circles inside the big circle with the positive signs denote your protons, and then the empty small circles in the big circle denote your neutrons, right? And then look at that big circle, the outer ring, right? The outer ring represents the electron orbital, right? Or the orbital. Right? So that is the probability of finding an electron within that region. Typically, we just draw it as a circle where you have your electron rotating around the orbital in that circular path. But we know that an orbital is just the probability, the range, or the region of having the highest probability of finding an electron. But for simplicity's sake, we're just going to denote it as a circle and say that the electron is floating around that circle. So let's go ahead and add those electrons. Okay, so now that we've added our electrons, right? Those two little circles on the outer side, on the outer big ring, right? Those two little circles represent our electrons. Now, what do we observe, right? Remember, electrons are negatively charged, right? So if we put those two electrons on the same side or in the same region of the orbital, right? Those electrons being negatively charged are going to cause a very temporary and partial negative charge on that side that they inhabit, right? And then on the counterpart, therefore, there must be a partial positive charge, right? So here we see a classic example of a dipole moment, right? You have a dipole moment forming when your electrons that are orbiting your orbital end up in the same region at the same time. Well, if that happens, you get a partial negative charge and you get a partial positive charge on two sides of the element. Now, let's say, for instance, we do the same thing we just did to the helium element on the left to the helium element on the right, right? So the same thing's going to happen. Those two electrons are going to be found in the orbital at the same region at the same time, creating that partial negative charge on one side, and therefore the other side is going to be a partial positive charge. And let's say, for the sake of this example, that the helium elements are orientated in the fashion that you see, right? That the electrons are located on the right side of the helium atom. Therefore, you can visualize the attraction between the partial negative and the partial positive. Now that we've added in our attraction in the green shade between the partial negative and the partial positive helium elements, now we see that this attraction between the negative sign and the positive sign are going to pull these molecules together. So that's what we mean by intermolecular forces. It's very important that you don't forget this foundational concept of the molecules being pulled together due to their electrons being located in the same region and the same proper orientation, allowing for attractive forces between those two molecules. Now, a couple things to note about London dispersion forces is that all molecules have London dispersion. Why? Because all molecules are going to have electrons floating around at some point, right? And those electrons are going to have a probability of landing in the same environment, creating temporary dipoles, right? But the biggest thing to remember is that these are very weak and temporary forces. Why? Because they depend on not only proper molecule orientation, but they also depend on your electrons being in the same region of the orbital, right? Remember that the orbital is mostly just empty space, right? So it depends on the electrons in the orbital being located in the same region, and that happening for a different molecule at the same orientation. Right? So you can see that this is very unlikely and very improbable. Therefore, it's a very weak and temporary force. So, guys, that's it for part one. Stay tuned for part two as we continue down the journey of understanding intermolecular forces.